And so in continuing the previous lesson, just finishing that up first, um, we talked about Newton's second law being F equals ma, but just to go back to Newton's first law, saying that a stationary object with no net force on it is going to remain stationary. And in the ideal case, when there's no friction, we could say a ball that's in motion would never stop rolling. That was Galileo's thought experiments, which we'll look at in class. Newton took those results of Galileo and generalized them in a single statement. An object that is at rest will remain at rest, and an object that is moving will continue to move in a straight line at constant speed if and only if the net force acting on that object is zero. So in the absence of a net force, an object will not experience acceleration. It'll be either at rest or in motion, depending on what frame you're viewing it in. So inertia is the tendency of an object to resist change. Inert meaning lazy, inertia being laziness, doesn't want to change its motion. Inertia is not a force because an object can't exert a force on itself. Remember, you need a net external force to change the speed or direction of an object. When something is in equilibrium, that's when it's not accelerating. It's either at rest or moving at constant velocity. And net force is something that causes the velocity of an object to change. So if that net force is zero, that's when we say the object is in equilibrium. So let's take a look at how we can apply Newton's second law. And this is kind of where today's lesson actually begins. How can we find the weight exerted on an object with mass m? Well, recall that in free fall, the only force you have acting on an object is gravity from the Earth or whatever planet the free fall is occurring on. So therefore, the sum of the forces, or the net force, is going to equal the force of gravity. So since the object accelerates, as we know, at a constant rate of g, or 9.8 meters per second squared, in the downward direction, the force of gravity is the mass times the acceleration. So the force of gravity is going to be m times g, or m times 9.8. And that's how we're going to find the weight of an object, is taking its mass and multiplying it by 9.8. So just to look at the system here, we have a marble falling with no air resistance acting up. So we know this purple arrow represents the acceleration is pointing downward, so the forces must add to point downward. So we know the acceleration is g, the mass is m. We don't know the force of gravity. That's what we just described. The net force is ma, and since the net force is also the force of gravity, we can know that the acceleration is g, and we have the force of gravity equaling m times g. Alright, so when you stand on a scale, you're not accelerating in any direction. So the force on you, the net force, must be zero. Therefore, since gravity is always pulling down on you, the spring has to exert an upward force that's equal in magnitude to your weight in the opposite direction, of course. The reading on the scale is actually determined by small springs in the scale that are calibrated to show how much force they're exerting on you. So therefore, this is the reason a bathroom scale measures your weight, not necessarily your mass. Because if you take this to the moon, the spring isn't going to have to exert as much force to oppose the moon's gravity pulling on you, so your weight is actually going to be less on the moon than it is on Earth. So let's take a look at an example here. We have Nuja holding a pillow with a mass of 0.30 kilograms, and if Sarah pulls horizontally on the pillow with a force of 10 newtons and Anuja pulls with a horizontal force of 11 newtons, what's the horizontal acceleration of the pillow? Well, we'll just call the direction to the right positive. We have two people pulling a pillow, and we're going to define that system as just the forces on the pillow, since we're trying to find the acceleration on the pillow, or of the pillow. So we'll call the direction to the right positive. The pillow has a mass of 0.30 kilograms, and the only contact forces are going to be the pull from the left and the pull from the right. So we can say in one direction we have 11.0 newtons, the other direction we have 10.0 newtons. We can see that since the right arrow should be a little bit bigger than the left, the acceleration is going to be to the right. Those are our contact forces. We also have the field force of gravity pulling downward. Each of them are actually going to be exerting a slight upward force to hold that pillow off the ground too, because we know that the pillow isn't accelerating to the left, it isn't accelerating up or down. It's only accelerating to the left or and right, because each is exerting a horizontal force. So they're each supporting that, and they might not be equal, but they're each holding it up as well, making sure that it's not falling to the ground. So net force, since up and down forces have to cancel out, the net force is going to be our 11 newtons minus our 10 newtons, which gives us 1 newton. And the mass of the pillow is, of course, 0.30 kilograms. So we're going to take our acceleration is equal to the net force over the mass, which is 1.00 newtons over 0.30 kilograms. We're going to find that that pillow has an acceleration of 3.33 meters per second squared. And that is in the positive x direction. So you could say it's positive 3.3 meters per second squared, or 3.3 meters per second squared to the right. But again, it didn't specify in the problem which direction the pillow is going, so we can just say 3.33 meters per second squared is the magnitude. So let's talk about apparent weight. Apparent weight is the weight that you feel. Your weight is always going to be your mass times your gravity, but you might not always feel that same force of Earth, knowing if you ride a roller coaster or even an elevator, your weight feels like it's changing. That's because you're accelerating. You're experiencing a different acceleration than you're used to. You're not experiencing Earth's acceleration. So whenever g changes on different elevations, you also feel a different weight. But g is relatively constant near Earth's surface. What we want to look at is what's happening on a scale, or what's happening on an elevator. What weight do you feel? Well, you can kind of see on a scale what weight you would feel, because if you stand on an elevator, let's say notice you're accelerating upward, so your velocity vector is increasing in the upward direction, and because you're accelerating upward, you know you have to have a net force upward. Your weight due to Earth's gravity is not going to change, so that means the scale has to exert a greater force on you to make you go upward. In other words, the floor of the elevator has to push on you harder than your weight is pulling down in order to cause that upward acceleration. So the apparent weight is the force exerted by the scale. It's pushing much harder than your weight, so you're going to feel heavier when the elevator is pushing you up. Let's say the elevator brakes, though. causing you and the scale to go in free fall. In this case, there's no force pushing up because the elevator's just in as much free fall as you are, and in that case the only force pulling down on you is the gravity, not this force upward on the scale, and you're going to feel weightless. The scale is going to read 0. Anytime you're in free fall, you're going to feel like you have no weight. That's when weightlessness occurs, when your apparent weight, when the weight you feel is 0 newtons. So let's say they get another example here. Your mass is 75 kilograms and you're standing on a bathroom scale in an elevator. Starting from rest, the elevator accelerates upward at 2 meters per second squared for 2 seconds and then continues at constant speed. Is the scale reading during the acceleration greater than, equal to, or less than the scale reading when the elevator is at rest? Well, when you're accelerating upward, the force upward at 2 meters per second squared, the force upward has to be greater than the gravitational force. So the normal force the elevator provides has to be greater than the force of gravity. On the other hand, when the elevator is at rest, you're not accelerating. Your acceleration is 0, and the normal force has to equal the gravitational force. They need to cancel each other out. So it's clear that the scale reading during the acceleration upward is going to be greater than the scale reading when the elevator is at rest. Let's talk about, we've been talking in the cases where air resistance is negligible, but as we know, air is always exerting forces all around us. If you think of a suction cup, you put a suction cup in, you remove the air from underneath the suction cup, and the air around it pushes harder than the air inside it. So we know that air is always exerting forces. Most of the time we can ignore it and still see the same effects. But an air is a fluid. Any gas or liquid is a fluid because it flows. So when objects move through a fluid like air, they experience what's called a drag force from the fluid. That drag force is going to cause it to lose energy and slow down. So the force depends on, this drag force depends on the motion of the object, also the properties of the object, such as its mass, as well as the properties of the fluid. Is it something like syrup? It's going to cause a much greater drag force than something like helium. You're going to be able to get through helium much easier than you can through syrup. So drag force will result in terminal velocity eventually. As the ball's velocity increases, the drag force, more air is going to be pushing up on the ball as it falls. So the drag force is whenever that enough air is pushing up on the ball, resisting the ball's motion downward to cancel out its weight, that's when you stop accelerating. You've reached your final velocity, your terminal velocity. So again, terminal velocity being whenever the drag force from the air is equal to the gravity going down. This could be at a high speed, a low speed. Again, a lot of divers or skydivers manipulate their orientation and how they're falling or jumping in order to change that terminal velocity. How fast do they want to be going when they no longer accelerate? So that concludes our second lesson on this force and motion chapter.